This video is sponsored by the Ecoflow Delta Pro. One of the biggest challenges renewable energy faces is a little problem called intermittency. The sun and wind can provide nearly endless supplies of clean power, but they don't always show up exactly when you need them. What if there was a clean renewable energy source that was as predictable as, say, the tides? Tidal energy systems have been around for a while, but we haven't seen them take off the way other renewable systems have. While experts project that tidal energy alone could power every house in the United States 2 times over, current tidal projects worldwide only power about 500,000 homes. But with new projects in Europe, Asia, and Canada taken off, are we about to see a new wave of clean, renewable, and affordable energy? Let's dive in. If tides have one excellent quality, it's that they are incredibly predictable. Humans have been able to predict tides with relative accuracy for over 2,000 years. Unless you're Bill O'Reilly.
Tide goes in, tide goes out. Never a miscommunication. You can't explain that.
Tides are also incredibly powerful, which is why they hold so much potential. To better understand why, here's a brief refresher on how tides work. Tidal energy comes from the gravitational force of the moon and, to a lesser extent, the sun. See, any two bodies out in space exert a gravitational force on the other. The equation looks like this. G is the gravitational constant, M1 and M2 are the masses of the two bodies, and finally we have R, the radius or distance between the two bodies squared in the denominator. This change in the force of gravity over distance is what we call the tidal force. This means that if two bodies are twice as far apart, the gravitational force felt between them is only 25% as strong. This is why even though the sun is way more massive, the moon, which is closer to us, exerts a larger tidal force. So how does the tidal force cause our ocean tides? Well, the strength of gravity depends on the distance, as the Earth has a radius of 3,958 miles, or 6,371 kilometers. The side of the Earth facing the moon gets pulled harder than the other, essentially stretching the Earth, especially our oceans. So this explains the bulge on the side closest to the moon, but what about the other side? Well, since the center of the Earth is closer to the moon than the far side, it's also getting pulled harder, again resulting in a bulge. Basically, the parts of the Earth facing and opposite the moon experience the strongest tidal forces, and the sides in the middle, the weakest. Coastal areas experience high and low tides every 6 hours or so as the Earth spins, resulting in 2 high tides and 2 low tides every day. This results in ocean water levels rising about 1 to 2 meters in areas of high tide. The sun also contributes to tides here on Earth. When the sun and moon are aligned, when we see a newer full moon, their forces align and we see super high and super low tides called spring tides. When the sun and moon are 90 degrees apart, the tidal forces cancel out a bit and we have neap tides. Finally, the moon's orbit isn't perfectly round, so it's closer to us at certain points than others, not by much, but when the moon is closer in its orbit and aligns with the sun, we have the highest tides possible called Proxygean tides. But what makes this tidal force so promising is that it's essentially an enormous wave of energy moving across the planet every single day without fail. Capturing tidal energy works a lot like capturing wind energy, basically taking wind turbines and placing them under the sea. Water is far more dense than air, over 800 times to be exact. That means that even with relatively slow current speeds, the turbines can still spin and produce quite a bit of electricity. Tidal energy systems fall into one of 2 major categories. The oldest and most common systems are tidal range systems, making up about 98% of all tidal energy projects worldwide. These systems use a large dam or range across a coastline with enormous floodgates at either side. Between the floodgates below sea level sits a row of enormous turbines. As a tide rolls in, the barrage gates open. As the water flows through, the turbines connected to generators rotate, converting their ocean's mechanical energy into electricity. Once the tide reaches its highest point, the barrage gates close, creating a large pool of water. This water can then be released slowly back into the ocean through turbines to create power on demand. In principle, these systems are very similar to pumped hydro, which we've covered in previous videos. But unlike these systems, which require electric pumps to push the water back uphill, these systems rely on the planet's natural tidal energy to pump water in and out. Because the turbines work at both directions, they can provide clean, reliable energy between 18 and 22 hours per day. Need power? just opened the floodgates. The oldest tidal range generator, La Rance, built in northern France in 1966, produces enough electricity to power the town's 250,000 homes and businesses. The second type of tidal energy system is called tidal stream, essentially underwater wind farms. They've been around since the 1970s. Large turbines connected to generators sit anchored to the sea floor, but the turbines themselves are closer to the surface. This makes them a bit more cost-effective since they reduce undersea construction. Floating stream turbines are among the most powerful in the world, with individual turn capacities of 2 megawatts. Scotland-based energy company Maygen is developing a 398 megawatt tidal stream project, the largest in the world. The initial phase involves 4 1.5 megawatt turbines connected to onshore power conversion units where the low voltage supply will be converted for export to local distribution networks. This initial phase will generate sufficient electricity to power 2,600 homes. As we mentioned earlier, since water is more dense than wind, these turbines can produce the same amount of power as a similar sized wind turbine, but with current speeds 1/10 the required wind speed. At speeds as low as 1 meter per second, these turbines can equal the output of a typical wind turbine. As current speeds increase between 2 and 3 meters per second, the turbines can access up to 4 times as much energy per rotor swept area as a similarly rated wind turbine. If tidal energy is sounding pretty good right about now, yeah, it's quite the win-win. Much like our sponsor this week, the Ecoflow Delta Pro. Did you know that since we installed the Ecoflow smart home panel and got 2 Delta Pros, our entire business has been 100% off-grid, running on sunshine and batteries. I even charge my Tesla about 25 miles a day, covering my usage, all from the sun. For Amazon Prime Day, Ecoflow has some pretty sweet deals, like $500 off this Delta Pro. I've had mine for about a year and I love it. Get 2 of them and a smart home panel and you can power your house, or just roll it around wherever you need it, or take it camping. With 3,600 watts of output, you can power nearly anything, and with 3.6 kilowatt hours of storage that expands all the way up to 10.8, you can do so for hours. But the real magic is when you add solar panels. With 1,600 watts of input, get some panels like I did and charge your batteries back up every day. These Prime Day deals are likely to be the biggest discounts Ecoflow has all year. So definitely check out the links in the description. Huge thanks to Ecoflow and you for supporting the show. A tidal range with 24 turbines has an installed capacity of 240 megawatts, or around 10 megawatts per turbine, with an annual output of around 600 gigawatt hours per year. That's enough power to sustain over 50,000 American homes, about the number of homes in my small town. How does this stack up to other renewables? Most onshore wind turbines have a capacity of between 2 to 3 megawatts, producing roughly 6 gigawatt hours annually. A modern-day offshore turbine comes a bit closer to roughly 8 megawatts, and the new record-setting Siemens Gamesa offshore turbines coming online in 2024 produce 14.7 megawatts. In the case of solar panels, they generally have output ratings roughly around 400 watts. To produce the same power as those 24 tidal turbines, you would need between 80 and 120 onshore wind turbines and 50 to 30 offshore turbines, or around 60,000 solar panels. But what about efficiency? Today's typical solar panels, as we've covered on this show many times, top out around 22% efficiency. And wind turbines, often heralded as the most efficient renewable, max out around 40%. Tidal turbines? Yeah, they absolutely dunk on the others, operating around 80% efficiency, nearly double that of wind. At this point in the video, we like to ask, if this technology is so great, why don't we see it everywhere? And indeed, there are a couple of things to consider. First, tidal energy plants don't currently have the major production infrastructure that other energy sources benefit from. That means tidal energy systems are by far the most expensive to build, requiring the highest capital costs up front. The reason for the cost is simple. As we've been saying, seawater is more dense than air. And while this helps tidal turbines produce more power, it also means they need to be made from more sturdy materials, not to mention the extra corrosive element of salt water. There's also the issue of what's called biofouling. Basically, as the machines live underwater, they're prone to buildup of a variety of sea life, which is great for the ocean, but can hinder the turbine's performance. So engineers have to factor that in when constructing and maintaining this technology. And then there's also the issue of impact on marine life. These tidal turbines can be moving pretty quickly, especially for how big they are. And what kind of impact can they have on whales and fish and sharks and other species? That would probably take a little more research to figure out, but that's something I think that people do have to consider when it comes to tidal energy. Some say that between these costs and other considerations, tidal energy plants are financially unviable. But what does the data say? According to the 2019 figures from the U.S. Department of Energy, the average commercial tidal energy project costs as much as $280 per megawatt hour to build. Wind energy, by comparison, currently costs roughly $20 per megawatt hour, making it one of the most lowest cost energy sources available today. But when it comes to energy, you can't just look at the base cost. Instead, you need to look at what's known as levelized cost, an economic measure that compares the lifetime cost of generating electricity across various technologies. In other words, it's not just about how much something costs up front, but how much power it can produce over its lifetime and how much maintenance it would require over that same period. Levelized cost is an important factor for consumers because it's one of the metrics by which the price of electricity is based. Now, there are countless metrics to determine levelized cost, but here are some averages based on numbers from the EIA. As you can see, depending on the technology, prices range between $30 per megawatt hour to about $170 per megawatt hour. Right now, the LCOE for commercial scale tidal energy projects falls between $130 to $280 per megawatt hour for tidal energy, which could certainly put it above the competition. But when you factor in longevity for these facilities, things start to look a little bit different. Modern coal-fired plants have an operating lifespan of more than 35 years. Yet environmental groups suggest that coal needs to be entirely phased out by 2040. Wind turbines and solar panels generally come with a warranty of 20 to 25 years, and while some solar cells have reached the 40-year mark, they typically degrade at a pace of 0.5% efficiency per year. Tidal energy systems are inherently age-resistant and have significantly longer lifespans. The average estimate for most tidal systems is 75 to 100 years. And significant cost reductions in LCOE are anticipated from the current stage of deployment to the commercial target of 61% for tidal energy. By 2030, it's possible that the base case scenario for tidal energy systems could come down as low as $75 per megawatt hour. But even at current prices, tidal energy systems are able to deliver power at prices equal to or less than other energy sources. Here are some current electricity rate averages for various production methods in the US. Generation costs for nuclear fall between 25 and 30 cents per kilowatt hour. Fossil fuel costs come in between 5 and 17 cents per kilowatt hour. Hydroelectric power is currently the cheapest form of renewable energy, costing just 5 cents per kilowatt hour. Wind power, which depending on the region competes with hydroelectric and comes between 2 cents and 6 cents per kilowatt hour, making wind power the cheapest depending on where it's installed. Solar power comes in at 6 cents per kilowatt hour, and electricity from natural gas plants roughly 6.5 cents per kilowatt hour. Though, as we covered in the geothermal video, lots of these factors can impact the price of natural gas. Now let's look at tidal energy. Estimated tidal energy from Canada's Nova Scotia Tidal Generating Station comes in at the most expensive, around 66 cents per kilowatt hour, compared to offshore wind in the same region, which comes in around 20 to 30 cents per kilowatt hour. So not looking great. But Laurence has produced electricity at a range from 4 to 12 cents since its inception. Now we're getting somewhere, and it's been operating since 1966. The Siwa tidal power station in South Korea, built in 2011, is the largest tidal range installation in the world, with an installed capacity of 254 megawatts. It produces electricity at 2 cents per kilowatt hour, which puts it among the cheapest of all energy sources. So sure, the impact tidal energy could have on your electricity bill depends on a number of factors, but to rule it out entirely, saying it's always the most expensive option, clearly isn't true. And of course, the numbers don't tell the whole story, because tidal energy produces electricity with zero carbon emissions. Obviously, natural gas and fossil fuels can't make that claim, despite sometimes being cheaper. And while other renewables may be able to produce energy at a lower price point, again, there's the issue of intermittency and an increased need for energy storage, because if the wind and sun aren't needed when it's shining or blowing, you got to store it somewhere. Otherwise, that energy isn't really all that useful. And the energy storage part of the equation is just a problem that tidal energy doesn't face. So not only is tidal a pure zero carbon form of renewable energy, but because it's a little more predictable, it requires less energy storage as well. And that's a price you can't really factor in without adding the cost of batteries to wind and solar. But cost isn't the only factor limiting the technology. There are also the issues of location. Tidal systems require coastlines, which already limit where they can be built, but not every coastline is optimal. See, tidal range systems benefit when the range sits around 7 meters. Any less, and the system becomes less economically feasible. The problem is that many of the areas with optimal conditions are in more remote locations where grid infrastructure may not already exist, which means larger upfront investment and potentially impacting local environmental regions. Still, despite these drawbacks, a number of countries have already begun to adopt tidal energy, and more projects are on the horizon. As they continue to prove themselves out more and more as an economically viable option, we may start seeing more of these systems popping up along our coastlines. So just like any form of energy generation, tidal energy systems will become more economically practical when we build them at scale. If you're only building a couple of these plants, yeah, it's going to be more expensive. But as more companies come online producing the parts and the blades and other components, these prices will come down. But there's also the issue of being housed in the ocean. How much maintenance will that take? How much more quickly will blades or other hardware degrade as a result of the corrosive salt water? These are the kinds of questions that only time will tell. But the good news there is we do have some of these older range plants like the one in France that have been around for a long time. So I think it's pretty optimistic that these things can last. But what do you think? Are tidal energy systems destined to become the next big wave of renewables? Or should we invest in other currently proven renewables? Sound off in the comments below. All right, so that is a look at tidal energy. There's some pretty awesome projects on the horizon that I'm pretty excited about. So thank you for watching. I'm Ricky with Two Bit da Vinci, and we'll catch you guys next week.